when objects collide, we know that momentum is conserved. But what about mechanical energy? So let's just review a little bit. Here's the road. Here's a road. And here's a vehicle right here, and it's this big Ford. Whoops. No, that's really bad there. Okay. Let's pretend like it's a Mr. Kane's Ford F-250 monster truck with a huge bumper on it. Okay. That truck really impresses me every time I see it. Then, here's my little Toyota Prius. And maybe I'm talking on my cell phone, which I should never do when driving, and I don't actually do it. But then I drift into the lane, and we're going to have a collision here. Okay? Yes. Well, okay, so when they collide, remember that they apply equal and opposite forces to each other, correct? Just because this truck is bigger than this little car does not mean the truck applies a bigger force to the little car. No. When two objects interact, they apply equal and opposite forces to each other. The effect of the force isn't equal, but the forces are nonetheless equal. And that force of collision happens for the same amount of time. So you got a force of collision times time, force of collision times time. They're equal and opposite in direction, which means the impulses are equal and opposite, which means the change in momentum are equal and opposite, which means there's no overall change in momentum for the whole problem. In other words, P initial equals P final. This is always true during a collision. But what about energy? This object was moving. It had kinetic energy. This object was moving. It had kinetic energy. Now we're not changing height here. So we're not going to transfer any of our kinetic energy into gravitational potential energy, and there's no springs here. So we're not going to transfer any of our energy into elastic potential energy. But when they smash together, what happens to some of the energy? How does it get transferred? Have you ever heard a crash? What do you hear? You hear a lot of noise. It's very loud. So some of the energy gets transferred in the environment as sound. Also, what happens to the stuff the vehicles are made out of? It gets crushed and bent. It takes work to do that. It takes energy. You don't think it takes energy to bend sheet metal? It does. So the sheet metal gets crunched. And what you end up with, okay, here's the truck again. Wish I could draw a better truck, but oh well. And then here's my little car. And okay, so all this metal got bent and squished, and that that took work, and it doesn't spring back. So there's no elastic potential energy there. It doesn't spring back. It's permanently deformed. Now, when you take a piece of metal and you bend it, and it doesn't spring back, I'll show you. I'm going to sacrifice this paper clip. So here's a paper clip, and let's say that represents the metal, some of the metal on this car. When you bend it, it took work to do that. Okay? And look, it didn't spring back. It's not stored up in the springiness of this metal. Where did the energy go? What happened to the work that I did? I transferred some of the energy out of my body into this paperclip. Where did it go? As what? Yeah, this will get hot, won't it? Have you ever bent a paperclip back and forth? If you go like this, take a paperclip and you bend it back and forth like this, just bend it back and forth and feel it. Yeah, it's a little bit hot. Not really hot, but if you do it a lot, it will get really hot. One thing you can do is take like a wire hanger and bend it back and forth, and you can get it really hot before it breaks. And so when you have a collision like this, the next time you're in a head-on collision, okay, get out of your car and feel the crumpled metal. It'll be a little warm. That's because all your kinetic energy is transferred into the random motion of the molecules of your destroyed car and disperses in the environment. It would be like if I took one of those beakers of water that I showed you and just dropped it and it just smashes all the energy released in the environment at one time. So what that means is this. Some of the energy gets dispersed in the environment, which means that let's talk about energy here. The initial mechanical energy of the system will be greater than the final mechanical energy of the system, right? This is the initial energy will be greater than the final mechanical energy. Why? Because we lost some of the mechanical energy, so we have less of it after the collision. Yes? We have a name for collisions where we lose mechanical energy, and actually there's no change in potential energy here, so the kind of mechanical energy we're really dealing with here is kinetic. So what we can really say is that the initial kinetic energy is greater than the final kinetic energy, and this difference in energy is dispersed into the environment through heating. This is called an inelastic collision. And an inelastic collision, we've lost some mechanical energy. However, what's true about momentum? Momentum is still conserved. So we can figure out, so that this delta K, if you go delta K, which is K final minus K initial, you're going to get some negative, some negative value of joules. It might be negative 5,000 joules. Why? Because we lost kinetic energy in an inelastic collision, and that negative sign will tell you that it's been lost from the system. Now, suppose, though, I see this coming, so I deploy my magical spring bumper. So, whoop, out comes a big spring out in the front of my car. And this spring will is such that when these two cars hit each other, you compress the spring and we do work on the spring. Now, unlike the metal in the inelastic collision, this metal is permanently crumpled. It's like this paper clip. It gets bent and doesn't spring back. But this spring will spring back. So it absorbs the energy of collision and stores that energy, that kinetic energy, in as elastic potential energy in the compressed spring. And then what does it do after the collision? Boing, it springs out. And thus, we get back all the energy we started with as kinetic energy. So if you have the before and after picture, the before and after picture what will happen is that we will keep all the, so let's say that we'll keep all our mechanical energy. And what that means is that if that spring is there, that K initial will equal K final. So you look at the kinetic energy before the collision, then after the collision, we'll have the same amount of kinetic energy. That is, if we have a spring on here, there's no friction in the spring. We don't hear any sound, by the way. It'll be a silent collision. You won't hear a doing. If you hear a doing, okay, you've lost a little bit of the kinetic energy that made sound. But this will just be, well, like silently.
Was you talking about a literal spring?
Yeah. I mean, it's not very practical, okay? This is one of those physicsy things in our imagination, right? Why would you do that? Well, because there are a lot of situations where we use springs to absorb energy and store it up so that we can get that energy back as mechanical energy. Well, you do have springs in the suspension of your car. And what it does is it absorbs some of the energy as your wheels go up and down and gives it back to you. But in any case, if this is true, now this is always true, right? P initial equals P final. This is always true. Momentum is always conserved. But if the kinetic energy doesn't change, this is called an elastic collision. Now, I must tell you, elastic collisions are extremely rare in nature. But they do happen, or at least there are collisions that are really close to being elastic collisions, and you can use them. You can use these two equations to solve problems. So here's the big idea. The big idea is this. If you have objects colliding, most collisions, we lose some of the kinetic energy in the environment through heating and sound and so on. But there are some collisions you can create that at least approach an elastic collision where you don't lose any kinetic energy. Kinetic energy before equals the kinetic energy after. Very rare, but they do happen. And you can use them to solve problems. And we will work some of those problems out. We'll work some examples of those later on. Okay.